Hello everyone, welcome to the lecture series on IC applications. Myself Sivaramakrishna, Department of ECE. In this lecture we are going to discuss about the analysis of differential amplifier. As we have seen in the previous lectures, the basic integrated circuit is nothing but operational amplifier, and you might notice the functional block diagram of the operational amplifier. It consists of several blocks, of which differential amplifier is the first stage and most important stage. So in the context of operational amplifier, we are going to discuss the differential amplifier. By this time you might remember, operational amplifier consists of differential amplifier as an important block in the circuit configuration. The contents of this presentation includes, if you notice, differential amplifier, so which we have seen in the previous lecture, and then basic types of differential amplifiers. That means what are the different modes available, within differential amplifier. After the definition of differential amplifier, we will discuss what are the different modes, nothing but with different configurations available for differential amplifier, and then coming to the analysis of differential amplifier. So if you remember the analysis of a basic amplifier, what is a basic amplifier? You might remember nothing but a common emitter amplifier. If you consider a common emitter amplifier, so it is required to analyze this particular amplifier. So that will be continued here, we can say. So the same components. So if you analyze any amplifier, we fix certain objectives. So for what purpose we need to analyze this particular circuit? So amplifier is nothing but an electronic circuit. For what purpose we are going to analyze? So if you remember, there are four basic components. What are they? One is nothing but AI, stands for the current gain, and then it is going to be the AV, voltage gain, and then it is going to be the input impedance, and the other is going to be the output impedance. These are the four key components we will analyze. These are the four key components for which we analyze the amplified circuit. It can be either your common emitter, common base, or common collector in the context of BJT. And if you look at the FET, so if you consider common source, common drain, or common gate, whatever it may be, these are the four basic components which we will try to analyze, which we will try to extract from, which we will try to analyze or obtain from the basic amplifier. Same thing, similarly, how we are going to analyze, what are the basic components of interest of this particular differential amplifier. Same thing we are going to determine. And then if you look at the next one, it is going to be the analysis. So once again we will go back to the amplifier and we will see that what is meant by the analysis. In what ways, what are the different ways available, what are the different ways to perform the analysis of differential amplifier. Is nothing but, it is a standard one actually. It is not only for differential amplifier. Even if you consider a basic amplifier, there are two ways. One is nothing but the DC analysis and another is going to be the AC analysis. If you consider any amplifier circuit, these are the two basic nature of the analysis. In fact, one is going to be the DC analysis and the other is going to be the AC analysis. In this lecture, we will try to finish and focus on the analysis of the differential amplifier in the context of DC. That is what, nothing but the DC analysis we will perform here. And coming to the basic circuit of differential amplifier. So we said in the previous lecture. So what is a differential amplifier? We are going to have two basic amplifier circuits, preferably in common emitter configuration. Here if you observe, this is going to be the first one and this is going to be the second one. So this is going to be the first amplified circuit and this is going to be the second amplified circuit. Both the circuits are operated under common emitter configuration mode. If you observe, this is our BJT base. This is a BJT based differential amplifier circuit. Both the circuits are BJT amplifiers and are operated under common emitter configuration mode. Both are in common emitter configuration mode. That is Q1. If you observe Q1 and Q2, there are two transistors. Unlike the basic amplifier circuit, here we are going to have two transistors. Two transistors are required to construct a differential amplifier. That's what we have seen. Right, differential amplifier consists of two number of transistors, namely Q1 as well as the Q2. Both the configurations, both the transistors are in common emitter configuration, both Q1 as well as in the Q2. And if you observe, the emitter terminals of both the transistors are tied together, are going to tie together through a resistor called RE. So what is the meaning here? Both the emitters of the transistors are tied together through the emitter resistance RE. And here we are going to provide the bias. This is nothing but the bias. What is this bias? This is nothing but VEE. Unlike the basic amplifier circuit, there the emitter terminal is connected to the ground in the case of your basic amplifier circuit. And here the emitter terminal is provided a bias of VEE, which is supposed to be a negative biasing here. So what is a statement we can draw here? Here this differential amplifier is going to have two number of bias. This is going to have two number of bias. What are they? One is the positive bias and another one is a negative bias. So what is your negative bias here? The negative bias is going to be the VE is the negative bias. And coming to the positive bias, where we are going to apply or provide the positive bias to this circuit. If you observe here, this is the collector terminal of the first transistor Q2, and this is the collector terminal of the first transistor. So that means both Q1 and Q2 collector terminals are tied together and provided a bias of VCC, which is going to be the positive bias. Here VCC is going to be the positive bias applied to the transistors Q1 and Q2. Of course, both Q1 and Q2 are having a resistance of RC, nothing but biasing resistance. Here RC1 as well as RC2, both are equal to RC, are nothing but collector bias resistors here, are supposed to be equal because we are going to have a symmetrical transistors. Both Q1 and Q2 are symmetrical in nature, where the biasing resistors RC1 and RC2 are going to be equal, should be equal, and their value is made as RC here. Right, this is the biasing section applied to this differential amplifier. So I will revisit this one. In the differential amplifier, we are going to have two number of transistors saying Q1 and Q2 and having two number of biasing voltages. So where negative biasing is provided to the emitter terminals of the two transistors and positive bias is connected to the positive bias is connected to the collector terminals of the two transistors. And coming to the input. So as we said, there are four different types of differential amplifiers. What are they? Are going to have. So let us see here. Coming to this particular differential amplifier circuit, we are going to have two inputs. One to the first transistor Q1 here is nothing but VBE1. This is nothing but VBE1. This is nothing but VBE1, and this is nothing but VBE2. VBE1 is because of the input applied to the first transistor Q1, and VBE2 is the input applied to the second transistor Q2 here. And what about RS here? Both RS are nothing but we can say input resistance, externally applied input resistance. The purpose is same, to avoid sudden increase in currents to the transistors. We need to provide some kind of a source resistance here. So what we can observe here, the two transistors are having inputs here. So one is your VBE1 and another one is the VBE2 due to externally applied input signal, due to externally applied sinusoidal input applied to both the input transistors. So this is the basic arrangement of this particular differential amplifier, which is considered for the analysis. Now coming to the analysis, as we said, we have two transistors, namely Q1 and Q2, and both the transistors are of the similar type. So are nothing but symmetrical in nature, and if you observe their characteristics, if you observe their independent or respective characteristics are going to be the same, are going to be the ideal. So what are the characteristics here? It may be your input characteristics or output characteristics, or parameters of alpha and beta are all going to be the symmetrical, are all going to be the same. That is the meaning for the symmetrical transistor. And also we said we have RE1 and RE2, that is the emitter terminals of both the transistors are connected to the resistor called RE. In fact, they are going to have the values of RE1 and RE2. They are tied together at a node here, So the net resistance of this RE is generally the parallel combination of RE1 and RE2. So what is the meaning here? Individually, every emitter is going to have a resistor here. Every emitter terminal is going to have a resistor here, and they are going to find, or they are going to meet at a point here where the circuit is going to ground here. So this is RE1 and this is RE2. They are connected at a point, and the net emitter resistance is assumed to be going to be the parallel combination of individual emitter resistance, that is RE1 and RE2. And another observation we made here is we have two collector terminals are coming from the two respective transistors. The way the values of RC and RC is given by RC1 and RC2, they are supposed to be the same. Both RC1 and RC2 are supposed to be the same here. And we said both the currents both measured across the individual transistors are going to be the same, that is VCC into IE and VE into IE. So these are some characteristics are highlighted, are obtained by knowing the nature of the two transistors. They are ideal in nature, that is the two transistors are matched and circuit is symmetrical here, right? So now we will start analyzing the circuit. So first we will consider the KVL. So you know about the KVL. So here the KVL is applied to the Q1 of your transistor. So if you observe the circuit here, the application of KVL leads to the equation called ICRS and then VBE at the input section, and another one is a 2 IARE, which is equals to VEE, This is the applied bias. This is equal to the applied bias. That is applied bias VEE is equals to. So what are the components? What are the components present in the input section? If you notice, there is input current, that is IB, coming from, that is through the source resistance RS, and there is VBE as input voltage, and the voltage due to the combination of the voltage due to the currents IE through the resistance RE are of course similar to be to be same. So we can make it as 2 IE into RE. So this is what the expression we can obtain after the application of KVL to the input section, KVL to the input of your first transistor Q1. And now if you look at the actual notations, that is we know that IC equal to beta IB and IC is equal to approximately IA. So if we substitute these things here, we can rearrange the equation, the first equation. So see here. So what we are going to have? We have IC is equal to beta IB, and you can extract IB out of this equation, saying IB equal to IC by beta. So what is it? IB is equals to, we can have IC by beta and then it is going to be IC by beta. We said IC is equal to IE approximately. So we can write this one as IE by beta. So IB can be rewritten or re-represented as IE by beta. And now substitute this IB in the first equation. So we are going to slightly modify the expression. Wherever we have IB, we are going to rewrite this one as IE by beta. So this will become IE by beta into RS plus VBE unchanged plus, and we have 2IE into RE. So what is the intention of rewriting this first equation is going to be this one. Let us express everything in terms of IE, and so that we can take IE as common. See here, see in this equation, after substitution of the value of IB, we can rearrange this first equation and you can take the value of IE as common. This leads to IE into minus RS by beta minus 2RE plus VBE. Of course, minus VBE. This is nothing but VEE is equals to IE into, so what we have, minus RS by beta, that is plus, in fact, plus 2RE plus VBE. So this is what the equation we are getting here, and this will be represented as the equation number 4. So far what we have done in this analysis, apply KVL to the Q1 of the transistor, apply KVL Q1 of the transistor in the input section, and we obtain an equation for IE. We obtain an equation for IE here, and now see this one. After simplification, so if you simplify the equation 4 here, what we are going to have, it will become VE minus VBE by, look at the denominator is purely RS by beta plus 2RE. So we are able to express the input current IE. We are able to express the current IE as VEE minus VBE by RS by beta plus 2RE after the simplification of equation number 4 here. And now we have some standard values for VBE. What are the standard values for VBE? It purely depends on the nature of the transistor which we use. So because the transistor can be a silicon or it can be your germanium. So these are the standard values. Of course, you need to remember these values. In fact, the value for VBE is going to be 0.6 or 0.7 for silicon transistor, and it is going to be 0.2 for germanium transistor. So we can rewrite this equation by substituting the value of VBE here. And moreover, see, look at this equation. So what we are going to have, there is another term called RS by beta. So we are going to substitute the values of VBE as 0.6 or 0.2 depending on the type of your transistor. Depending on the nature of the transistor, we will replace the value of VBE. We have one more component, that is RS by beta. So what is the value of beta in general? Especially if you are dealing with the transistor which is in common emitter mode. This will be definitely a large one. The value of beta will be somewhere around 50 or 100 something. So let us look at the nature of RS by beta. So what is the value of RS by beta here? So in the denominator, we have two components. What are they? One is RS by beta and the other is 2RE. Let us consider the value of RE as at least a few kilo ohms. The value of RE can be at least a few kilo ohms. And what is the value of beta? Let us say it is going to be the 100. RE is, let it be some 1 kilo ohm. Let RE be 1 kilo ohm. That is, RE is equals to 1 kilo ohm and beta as 100. What about the value of RS? Will be of the order of hundreds of ohms. It can be 100 ohm or 200 ohm. However, it can be even, you can say 200 ohms. it can be a 200 ohms. Now look at this fraction here. So what we have in this term here, it is going to be 200 by 100. So what is the value here? It is going to be 2. What about the value of 2RE here? So here this is going to be 2 kilo ohms. So what is the assumption we can draw here? RS by beta is generally very small when compared to 2RE. Since in the denominator we are going to have two terms. One is RS by beta and other is 2RE, of which we can easily neglect this RS by beta because of its small nature, because of the value which is very small when compared to 2RE, when compared to the other term. So we can neglect this and the denominator is left with 2RE only. So we are going to rewrite the expression for IE. We are going to rewrite the expression for IE. We are going to rewrite the expression for IE by eliminating, nothing but by assuming, since its value is very small, so you can easily neglect RS by beta here. So what is the equation now? Now the IE becomes, IE is equals to VEE minus VBE by 2RE, right? And now determine the expression for VCE. See, we are going to perform DC analysis. So in this analysis, the key focus is determining the Q point or operating point of the transistors, right? So we find the expression for IE. Of course, this leads to IC. And now we need to find the other term. What is the other term? VCE. We need to find VCE because the Q point consists of two parameters or two components. What are the two components? One is IC, another one is VCE. So if you remember the characteristics diagram of your transistor, so here is your IC and here is your VCE. Is it right? No. So what is correct now? So it is going to be the relation between applied voltage to the current. That is, applied voltage is your VCE and it is going to be the IC. These are not the applied voltage, in fact. These are the output voltage versus output current. So where we can draw the output characteristics of the transistor, right? So now what is your Q point here? It is going to be the VCEQ and ICQ. So the Q point consists of, it has two coordinates. One is the X coordinate and another one is the Y coordinate. X coordinate is going to be the VCEQ and Y quadrant is going to be the ICQ. So since we find IE, it indirectly measures or provides the value of IC because IE is approximately equals to IC here. IE is approximately equals to IC. Now we will try to find the expression for VCE. So look at the output section of your differential amplifier where we have VCC, biasing voltage VCC. So VCC can be written as like this. So how can I write VCC here? So VCC can be written as in terms of the collector voltage and in terms of the collector current. So that is, VCC can be written as VC plus IC into RC. That is the collector voltage, the biasing voltage can be expressed as the components of collector voltage and its current. That is VC plus IC RC. So that can be written as VC is equals to VCC minus IC into RC, taking the other component on the other side, right? And now you can find the expression for VCE. So once you know VCC, you can find the expression for VCE. What is VCE now? VCE can be written as VC minus VE. VC minus VE will be the value of your VCE. So do remember VCE. It is a voltage measured across the collector terminal and emitter terminal. So it can be measured as VC minus VE. And now we already determined the value for VC. What is the value for VC here? VC is going to be the VCC minus ICRC. Substitute the value of VC here. So what we will get here? VCC minus ICRC minus VE. And again we are going for one more approximation or assumption. So just look at the statement here. So after neglecting any drop across your RS, source resistance, V is equal to VBE. So what we are going to say here, if you neglect any drop, assuming there is no drop across the source resistance, the VBE will be VE. So we can rewrite that as VBE here. VE is going to become VBE here with this assumption. Try to understand these assumptions. Here we made an assumption. What is it? There is no drop. Neglect the drop across the source resistance RS. Then VBE is equal to VE. So rewrite the expression once again for VCE. So we start with the expression saying VCE is equal to VC minus VE. And we substitute the value for VC. What is the value of VC? Whatever obtained from the biasing voltage. And then considering the basic assumption, we said VE is equal to VBE. So the equation will become VCE is equals to, if you observe, it is going to be VCC plus VBE minus ICRC, right? And hence we can say that IE is equal to IC. After all this discussion, we can say that IC is equal to IE, and we find the expression for VCE. This is sufficient to determine the quiescent point of this particular differential amplifier. So what we said, IE is equal to IC, which in turn gives the Q point, that is ICQ. And also VCE is obtained, that is nothing but VCQ. So we have both quadrants here, right? So what is your Q point here now? Q consists of two quadrants. What are they? VCEQ and the other is ICQ. Both the quadrants are obtained by performing DC analysis. So you must understand the purpose of DC analysis. See, in any amplified circuit, the analysis is made in the context of DC as well as in the context of AC. So again, one more point you need to remember, DC analysis is made by suppressing all the AC components present in the circuit. So DC analysis is made by suppressing all the AC components present in the circuit. So go back to the basic differential amplifier circuit, that is the equivalent circuit drawn in this lecture. So what is your equivalent circuit? If you observe, there is no AC component here. There is no AC component. All the AC components are suppressed. That means are connected to the ground. Right? So this is the first step. If you want to perform the DC analysis, DC analysis is made by suppressing all the AC components. Right? And what is the objective of the DC analysis? What is the objective of DC analysis? It is to find the Q point. Q point is nothing but the operating point of your amplified circuit. By determining the two quadrants, what are the two quadrants? VCEQ and ICQ. You can find the quiescent point or operating point. That means in which region you want to operate your differential amplifier. So region means the amplified circuit can operate in three basic regions, right? What are the three basic regions? It can be there are three regions of operations. What are they? One is going to be the saturation region, and another one is going to be the cutoff region, and the other is going to be the active region. So these two regions are usually operated if you want to operate the circuit, the transistor circuit as a switch. And the third one, whatever we said, is it is the region, suitable region to operate the transistor in active region. It must be a amplifier. If you want to operate a transistor as an amplifier, we need to fix the Q point in the active region, right? So, and finally we reach the destination, conclusion of your DC analysis. Purpose we defined, purpose of DC analysis is nothing but determine the operating point or Q point of the differential amplified circuit, and we have seen the steps how to perform the DC analysis. That is by applying KVL to the input and KVL to the output ports of your differential amplified circuit, and by letting some standard assumptions we are able to find VCEQ and ICQ. So here is your expression for ICQ. What is the expression for ICQ here? VEE minus VBE by 2RE. This is your ICQ, and VCEQ is going to be the VCC plus VBE minus ICQ into RC. So these two will set the operating regions of your differential amplifier, right? So this is nothing but your DC analysis, and then similarly we can perform the AC analysis of the differential amplifier. So the AC analysis of the differential amplifier will be seen in the next session. So before concluding this session, I will brief the AC analysis. What we are going to do, how we are going to perform the AC analysis. It is just a reverse operation, I can say. In the DC analysis, all the AC components were suppressed, and in the case of your AC analysis, all the DC components will be suppressed, right? So that is the first step here. So in AC analysis, we will calculate what we are going to calculate. Once again, go back to the AC analysis of basic amplifier. What we are going to determine, what we are going to determine in the AC analysis, we said no, it is all about the gain. So do remember, in the AC analysis, one can determine the values of gain. What values of gain? It can be your voltage gain. That's what we said, AV, and it is going to be the AI. AV and AI are going to be the voltage and current gains of your amplifier. So if you want to determine these gain values or gain expression, values is nothing but get the expression first. Get the expression for voltage gain and current gain. Then you can determine the values automatically. By substituting corresponding values of the resistors and currents you can get. That's not a big deal in fact. So in AC analysis, the purpose of the AC analysis is to determine the gain expression. That we are going to achieve in AC analysis. The first step remains same. What is the first step? Suppress, ground all the DC components present in the amplified circuit, right? And here that the nature of the gain or the type of the gain which we are going to determine is somewhat different when compared to your basic amplifier, because in basic amplifier, if you consider a common emitter or common base or common collector, it is only a single transistor. There we use only one transistor, we have only one Q1, and here we have two transistors, that is Q1 and Q2. So here the gain which we are going to measure is going to be the differential gain. That is a first gain parameter, and the other gain parameter is going to be the common mode gain. So what kind of gain expressions or values we need to determine while analyzing the differential amplifier is, one is the differential gain and the other is going to be the common mode gain. So these are the two gain expressions or values we are going to determine under AC analysis. By performing AC analysis, we are going to determine the expressions for differential gain and common mode gain. So we will see this analysis, the AC analysis, in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.